In 1977, NASA launched 2 spacecraft intended to operate for only a few years. Their mission was simple: fly past Jupiter and Saturn, transmit data, and disappear into history. Instead, NASA sent humanity on the longest journey we've ever undertaken. Today, Voyager 1 is more than 150 astronomical units from the Sun. It's already crossed the heliopause, the boundary where the influence of the solar wind ends and the interstellar medium begins. And it was there that something strange happened. Sensors recorded a sharp change in plasma density. Magnetic fields suddenly changed character. Cosmic radiation increased. Voyager didn't see anything with its eyes, but the physics of space around it changed. This was humanity's first direct contact with interstellar space. But here's the important thing. Even now, after almost half a century of flight, Voyager is still within the Sun's gravitational sphere. It has left the solar wind bubble, but it hasn't left the solar system. Between Voyager and the true boundary of our solar system, there are still thousands of years of travel. And it is there, in near total darkness, that a hypothetical structure we've never seen directly lies. A giant sphere of trillions of icy bodies. A cosmic graveyard of primordial matter. The source of the comets that occasionally light up our skies. What we call the Oort Cloud. It all began with the launch. The moment a fragile machine with incredible precision set out on a journey no one had ever attempted before. Voyager 2 was not just any spacecraft. It was humanity's first envoy to the outer planets. A silent observer tasked with uncovering the secrets of worlds we could barely imagine. Its trajectory took it past gas giants and icy moons, revealing environments that seemed practically alien in their strangeness. The data sent back to Earth forever changed our understanding of these distant worlds. Voyager revealed Jupiter's raging storms, Saturn's intricate rings, and Neptune's supersonic winds. But it was the brief encounter with Uranus, the least studied of the giants, that left us with the most enigmatic mysteries, secrets hidden in the planet's magnetic field, its moons, and its strange lopsided tilt. Voyager's journey may have concluded decades ago, but its discoveries still resonate with the questions we ask today. And today, by revisiting its data with modern technology and fresh perspectives, we're uncovering things about these worlds, namely Uranus, that Voyager itself could never have imagined. The flyby over Uranus performed by NASA's Voyager 2 spacecraft in 1986 was a milestone in our exploration of the outer solar system. For the first time, we had the chance to closely observe this distant, mysterious planet. Its blue-green hue, faint rings, and tilt so unique that Uranus rotates around the Sun like a rolling ball. However, beneath the stunning images and data gathered during this encounter are findings that suggest the understanding we gained from Voyager's observations, particularly of its magnetosphere, may need to be revisited. The journey of Voyager 2 to Uranus occurred under atypical conditions. The spacecraft arrived just days after a rare and intense burst of solar wind, a high-energy surge of charged particles from the Sun that compressed the planet's magnetic field to a fraction of its normal size. Solar wind, a constant stream of charged particles from the Sun, usually shapes planetary magnetic environments, creating magnetospheres that shield worlds from harmful solar radiation. But in this case, the solar wind's intensity was so high that it compressed Uranus's magnetosphere to about 20% of its usual volume, significantly skewing the data the spacecraft could collect. According to a recent study published in Nature Astronomy, Such circumstances are rare, occurring only about 4% of the time. Had Voyager arrived a week earlier, it would have observed a much larger magnetosphere, more in line with those of other giant planets like Jupiter, Saturn, and Neptune. Previously, scientists believed that Uranus's magnetosphere was unusually weak, with low plasma concentration and highly energetic radiation belts. Plasma, a state of matter where atoms split into charged particles, is a common feature of other planets' magnetospheres, particularly those with strong magnetic fields. Voyager's data suggests that Uranus's magnetosphere lacked plasma from the solar wind and its moons, leaving its plasma environment abnormally sparse. However, new analysis points to a different conclusion. The solar wind likely suppressed plasma presence in the planet's magnetosphere, leading to the mistaken belief that Uranus was devoid of a significant plasma. At the outer boundary of our solar system, far beyond Pluto, there is a giant invisible structure. Imagine a spherical shell of space inhabited by billions or perhaps even trillions of ancient icy objects. This swarm represents the farthest boundary of the influence of our Sun. It is drawn in all diagrams. It is spoken of as something taken for granted. However, there is one paradoxical nuance. We've never seen it. Not once. Humanity knows less about it than about neighboring star systems. So why are scientists so confident in its existence? And what if they're wrong? What do the orbits of ancient comets, decades of astronomical calculations, and recent discoveries really tell us? Could other star systems hide similar structures? Or have we misunderstood something fundamental about our own? Every time a comet passes near the Sun, part of its icy surface evaporates, forming the beautiful tail that we see. However, there is a catch. If a comet repeatedly visits the Sun, their ice should eventually be depleted. So where do these comets come from? And how do they survive for billions of years? Astronomers concluded that comets must spend most of their lives far away from the Sun's heat, in a cold storage region at the outskirts of the solar system, and only occasionally visit the inner regions. Another clue was the orientation of cometary orbits. Unlike the planets, most of which orbit in nearly the same plane, and the short-period comets from the Kuiper Belt, many long-period comets appear from all directions at different angles. These icy visitors can arrive from above, below, or at any angle relative to the planetary plane. Such random inclinations suggest that their source is not a disk, like the asteroid belt or the Kuiper Belt, but a distant spherical reservoir surrounding the Sun. By the middle of the 20th century, all the conditions were in place for the proposal of a bold hypothesis that could resolve this mystery. As early as 1705, Edmund Halley determined that the bright comet observed in 1607 and 1682 was in fact the same object, returning on an orbit with a period of about 75 years, now known as Halley's Comet. This proved that at least some comets repeatedly orbit the Sun and raised a profound question. How could Halley's Comet return for thousands of years without disintegrating? The logical answer was it spends most of its time far from the Sun, preserving its ice in the deep freeze of space. Fast forward to 1932, when the Estonian astronomer Ernst Öpik proposed a bold idea. Perhaps a vast cloud of cometary bodies exist at the edge of the solar system, serving as a reservoir to replenish comets. The concept remained largely unnoticed until 1950, when the Dutch astronomer Jan Oort independently viewed it and became armed with new data. Oort studied long-period comets, those that orbit the Sun over thousands or even millions of years, and noticed something strange. The farthest point of these comets' orbits, their aphelion, tended to cluster at a distance of about 50,000 astronomical units from the Sun. That's roughly 4.5 trillion miles. an unimaginable distance, yet still gravitationally bound to our Sun. These comets were not arriving from interstellar space. They were far too close for that. But it was also clear that they did not originate from any known planetary region closer to Earth. For Oort, this data pointed to the existence of a vast cloud of icy bodies orbiting the Sun at distances of tens of thousands of AU. In his 1950 paper, he proposed the theory of a thick bubble of swarming icy debris surrounding the solar system. This idea elegantly explained two things at once: why long-period comets arrive from all directions, and where they are when they are not visible. The hypothetical cloud of comets soon became known as the Oort Cloud. Oort's hypothesis, despite being radical for its time, has withstood the test of decades. Although we still have not directly observed the Oort Cloud, it remains the leading explanation for the origin of long-period comets, supported by extensive calculations and computer models. But first, to understand how unusual the Oort Cloud is, let's recall the structure of the solar system as we know it. Planets from Mercury to Neptune orbit in a flat plane, the ecliptic. Between Mars and Jupiter lies the asteroid belt, a band of rocky debris. Between Neptune, roughly 30 AU from the Sun, lies the Kuiper belt, and this is an extensive ring of icy objects and dwarf planets like Pluto, extending roughly to 50 AU. Both the asteroid belt and the Kuiper belt are disc-shaped and confined to the ecliptic plane, orbiting in the same direction as the planets. These regions are also relatively close to our star on a cosmic scale. Beyond the outer edge of the Kuiper belt, the solar system does not end abruptly, but becomes extremely empty. This is a sparsely populated zone known as the scattered disk, extending several hundred more astronomical units. Data from NASA's New Horizons probe suggests that some Kuiper belt objects were gravitationally ejected into eccentric objects reaching up to 1,000 AU. Nevertheless, at a distance of around 1,000 astronomical units, we're barely 1% of the way to the proposed Oort Cloud. The inner Oort Cloud is thought to begin roughly 2,000 to 5,000 AU from the Sun. The main part of the cloud extends out to 50,000 astronomical units or more. Such numbers are truly counterintuitive. For context, one astronomical unit is the distance from the Earth to the Sun. 50,000 AU is roughly 0.8 light-years, almost a fifth of the distance to the nearest star. And according to some estimates, the farthest part of the Oort Cloud may reach up to 1.5 light-years, over 100,000 AU. In fact, this structure could extend from a quarter to half the distance to the nearest star. It's precisely this fact that makes it the most distant region of the solar system. Even our fastest spacecraft would need millennia to traverse these distances. For example, NASA's Voyager 1 and Voyager 2 probes are farther from Earth than any other human-made objects. After more than 48 years of travel, in 2026, Voyager 1 is about 159 astronomical units from the Sun, far beyond Pluto, but still nowhere near the Oort Cloud. At its current speed of roughly 17 kilometers per second, Voyager 1 would reach the inner edge of the cloud in about 300 years, and traveling beyond it would take 30,000 years. By that time, its instruments would long be non-functional. In other words, if future scientists send a dedicated probe to this structure, they'll never live to see it arrive. The scale of the cloud is not just vast, it's practically interstellar. Imagine an ancient icy wanderer that spent tens of thousands of years in the frigid darkness at the edge of our solar system and is now headed straight for us. In 2025, the Pan-STARRS automated telescopes first spotted the faint glow of this distant object. Since then, it's been steadily approaching the center of our solar system, the Sun itself, and Earth. This object, named Comet C 2025 R3, is unusual not only for its trajectory but also for its fate, which could soon become the main celestial show of the year. According to astronomers' calculations, on April 20, 2026, the comet will pass perihelion, its closest point to the Sun, at a distance of approximately 0.51 astronomical units, just 100 million kilometers from our star. A week later, on April 27th, it'll reach its closest approach to Earth at a distance of approximately 0.53 AU, still safely distant, but close enough to be visible in the night sky. The orbit of C-2025-R3 itself is highly unusual. It is inclined by approximately 125 degrees relative to the plane of the ecliptic, meaning the comet is moving retrograde, opposite the motion of the planets. Such sharply inclined trajectories are a classic sign of bodies originating from the distant Oort Cloud. And its position between the Sun and Earth could create an effect which the comet's dust tail directly reflects sunlight back toward us, turning a dim object into a bright, glowing trail in the sky, perhaps even visible to the naked eye if the nucleus ejects enough dust. So when you look up at the sky in the spring of 2026, remember, this visitor from the Oort Cloud is more than just a beautiful sight. It's a window into the most ancient history of our solar system, an icy messenger from its most distant and unexplored depths. And now let's take a closer look at what we know about solar wind. When these charged particles interact with a planet's magnetic field, they exert pressure that can compress, expand, or even reshape the magnetosphere. This interaction is not static. The conditions of the solar wind are constantly changing under the influence of factors like solar activity and the planet's distance from the Sun. On planets with strong magnetic fields, such as Earth, Jupiter, and Saturn, the solar wind can significantly influence their magnetospheres, creating protective shields that guard the planet from harmful radiation. The magnetosphere is essentially a planet's defense system shaped by its internal magnetic field. It acts as a shield, deflecting and redirecting charged particles. However, the system is not impervious. The strength and size of the magnetosphere depend largely on the dynamic pressure of the solar wind, which varies in intensity and velocity. At the time when Voyager 2 completed a flyby of Uranus in 1986, conditions were extreme, as the dynamic pressure of the solar wind was at its peak. The dynamic pressure of the solar wind is the product of the solar wind's mass density and the square of its velocity. Under normal conditions, Uranus's magnetosphere extends about 22 to 25 planetary radii from the planet. However, during the flyby, the magnetopause, which is the boundary where solar wind pressure balances the planet's magnetic pressure, was compressed to 17.3 RU. As solar wind pressure increased in the days leading up to the flyby, the size of the magnetosphere decreased significantly. This compression not only affected the magnetopause, but also likely influenced the unusual behavior of the planet's radiation belts. Typically, radiation belts around planets are formed from plasma sourced from the planet's atmosphere, moons, and the solar wind. The intense solar wind during Voyager's approach likely pushed plasma out of Uranus's magnetosphere, leaving the region depleted and altering the typical behavior of its radiation belts. As a result, an unexpectedly intense belt of electron radiation appeared, puzzling scientists for decades until new findings emerged. Astronomers proposed the theory that the Oort cloud actually has a two-part structure. The outer part is a classical spherical shell extending roughly from 20,000 AU to the farthest reaches at 50,000 AU and beyond. The objects in the outer part are weakly bound by the Sun's gravity, and over millions of years their orbits have formed a giant sphere. Closer to the Sun, there may be a denser inner Oort cloud, also called the Hills cloud, extending roughly from 2,000 to 20,000 astronomical units. Scientists suggest that this inner region may be more disc-like or torus-shaped, somewhat resembling a puffed-up Kuiper belt. Objects in the inner cloud are held slightly more strongly by the Sun and may not have fully dispersed into a sphere. Instead, they form a dense disk or ring of material beyond the scattered disk. Why do we think there's two regions? One reason is gravitational binding. Objects located a few thousand AU away still experience strong enough attraction from the star to remain in a relatively flattened distribution, while those very far away, over 50,000 AU, are so weakly bound that passing stars and the tidal forces of the galaxy can scatter them in all directions. Computer simulations support this idea. They show that early in the solar system's history, close stellar passages in the tidal gravity of the Milky Way could have disrupted the orbits of distant planetesimals, rounding the orbits of the outermost ones into a nearly spherical cloud, while the inner part, being more tightly bound, could have preserved a more original disk-like shape. In short, the Oort cloud may consist of an outer spherical shell and an inner toroidal band coexisting together. Together, this two-tiered cloud may contain countless icy bodies, from tiny comet nuclei to a few miles across, and to much larger, more substantial objects. But what exactly are the objects in the Oort cloud made of? Judging by all the comets we've observed, the vast majority of them are a mixture of ice and dust. Roughly speaking, frozen mud balls. Scientists believe that the bodies in the cloud consist of volatile ices such as water, carbon dioxide, methane, ammonia, and carbon monoxide, mixed with rock and organic compounds. Estimates suggest that the cloud contains hundreds or billions or even trillions of such icy bodies. Many of them are relatively small, though some may reach tens of miles in diameter or more. Some researchers even propose there could be a few large enough to be considered dwarf planets, but more on that later. Until recently, virtually all known objects arriving from the Oort cloud were icy and appeared as comets when approaching the Sun. But in 2021, astronomers received a dramatic surprise. A fireball meteor observed over Alberta, Canada, was traced back to the outer part of the solar system. To everyone's astonishment, it was made of rock, not ice. This meteoroid, roughly the size of a grapefruit, penetrated the Earth's atmosphere much deeper than an icy comet fragment would, indicating its density and rocky composition. Its orbit was calculated to resemble that of a long-period comet with a high inclination and even retrograde motion, exactly what one would expect from an object originating in the Oort cloud. Scientists were surprised to discover that this object, despite its place of origin, was rocky, contradicting the assumption that the cloud contains only frozen debris. How could this happen? The leading theory suggests that in the early stages of the solar system, some rocky bodies from the inner regions were ejected and mixed with ices in the Oort cloud. In fact, recent studies indicate that a few percent of the cloud's population may be asteroids, rocky in nature, rather than exclusively comets. If the Oort cloud contains trillions of objects, why have we never seen a single one of them? The answer is simple: distance and faintness. Since the bodies in the cloud are on average only a few miles in diameter and are so far away, the resolution required to detect such a small object is beyond current technological capabilities. A typical Oort cloud object is no bigger than a mountain, while it's located at a distance from the Sun more than 50 million times its own size. It's like trying to see a snowball from tens of billions of miles away. Even the closest objects would appear incredibly dim. Unlike stars, which generate their own light, or planets closer to the Sun, which reflect enough sunlight to be detected, Oort cloud bodies are dark and inert. These objects are invisible against the blackness of space. Moreover, today we can barely observe dwarf planets in the Kuiper belt at distances of around 50 AU and widths of hundreds of miles, and yet they reflect some sunlight. Beyond the Kuiper belt, even the combined glow of billions of Oort cloud comets would be too diffuse and faint to be detected. Given such vast unexplored territories in the outer solar system, it's no surprise that scientists and dreamers have speculated about unknown planets hiding out there. One of the well-known hypotheses was a giant planet nicknamed Tyche, proposed in 1999 by two astrophysicists. They noticed slight anomalies in the orbits of some long-period comets and suggested they might be perturbed by a hidden gas giant, possibly several times more massive than Jupiter, located in the Oort Cloud. Tyche was hypothesized to orbit at a distance of 10 to 20,000 astronomical units. However, this idea remains speculative. In 2010 and 2011, NASA's WISE infrared space telescope conducted an all-sky survey sensitive to large cold objects even at such distances. WISE found no evidence for a Jupiter-sized or larger planet in the outer solar system, effectively ruling out Tyche's existence. Nevertheless, the idea of hidden worlds at the edge of our system persists in other forms. More recently, astronomers have discussed the existence of the so-called Planet 9 or Planet X, a super-Earth or mini-Neptune, possibly 15 times the mass of the Earth, but likely located on the inner edge of the Kuiper Belt. That, however, is a separate story, and, by the way, we've already made a video about it. However, the question, could there be planet-sized objects in the Oort Cloud, remains pressing. It's not entirely impossible. A 2023 study examined this question from a different perspective: the capture of wandering planets. Computer simulations showed that when stars form in clusters, as the Sun did, they can capture planets ejected by one another. Captured worlds typically end up on the outskirts of the new star system, essentially in the Oort Cloud region. Researchers estimated that the probability of our Sun captured the planet the size of an ice giant early in its history is about 7%, and that such a planet could still be hiding in the cloud as an adopted planet. Interestingly, they also found that such a planet is more likely to have been captured as a rogue from another star than ejected from the Sun's original planetary system. They estimated the probability that one of the Sun's initial planets was thrown to the outskirts at only 0.5%. However, even a 7% probability means that it's still quite possible that no large planets exist there at all. At present, we have no direct evidence of any large object in the Oort Cloud. If there were one, we would have likely already detected some gravitational effects or a faint infrared glow. Nevertheless, although the cloud itself is invisible, it speaks to us through the comets it sends inward. Among astrophysicists, it's widely believed that long-period comets with orbits longer than 200 years originate from this region. These include some of the most spectacular comets ever recorded in history, bright phenomena that seem to appear out of nowhere and do not return for thousands of years, if ever. When a distant Oort Cloud object receives a gravitational nudge, whether from a passing star or the galactic tide, it can begin a slow journey toward the Sun, falling inward along an asymmetrical, elliptical orbit. After millions of years, it finally reaches the inner solar system as an entirely new comet. Such events are rare on human timescales, but over millions of years, a steady stream of comets flows through our system. Most observed long-period comets have been seen only once in history. Their return periods are so long that civilizations rise and fall in the meantime. Some comets have orbits so lengthy that the last time they passed through the inner solar system, modern humans did not yet exist on Earth. Others are on trajectories that will never return. The Sun gives them a final gravitational push out of the solar system, turning them into interstellar wanderers. An interesting subtype is the so-called Halley-type comets. They have intermediate orbital periods from 20 to 200 years, but unusual, highly inclined or retrograde orbits. They are all named after Halley's Comet, which despite its roughly 75-year period, is believed to have originated long ago from the Oort Cloud. Such bodies likely began as long-period comets whose orbits were captured into shorter loops by gravitational encounters with the giant planets. This explains why Halley's Comet and its relatives do not orbit along the plane of the ecliptic-like typical short-period comets. They were born not in the Kuiper Belt, but in the Oort Cloud, and later redirected inward. Yet one might wonder, could some of these long-period comets actually come from outside the Oort Cloud, beyond our solar system? Indeed, the first confirmed interstellar comet, 2I Borisov, was observed in 2019, and it was on a hyperbolic trajectory unbound to the Sun. Borisov's composition, rich in carbon monoxide, hinted that it formed around a different type of star. Earlier in 2017, an even more enigmatic object, Oumuamua, was discovered, another interstellar visitor. These cases show that some comet-like objects originate from beyond our system. However, such visitors are extremely rare. The vast majority of long-period comets follow the expected pattern if they come from the reservoir of the Oort Cloud around our Sun. Their orbital distribution, inclination, and the fact that we see far more long-period comets than interstellar ones all confirm that the cloud is real and populated. Every long-period comet that graces our sky once in a lifetime is essentially a messenger from this dark, distant place, providing indirect evidence of its existence. Earlier, we noted that comets from the cloud arrive from all directions, forming an almost uniform sphere around our star. This spherical shape is a key aspect of the Oort hypothesis. But why a sphere and not a flat planetary disk? The answer lies in billions of years of gravitational nudges. In the early solar system, the precursors of the cloud were planetesimals ejected by the gravity of Jupiter and the other giant planets. Initially, these objects moved along elongated orbits, still roughly within the original plane of the solar system. However, over time, two main factors randomized their orbits: passing stars and galactic tides. Our Sun was born in a star cluster, which means that during the first few 100 million years, neighboring stars frequently pass by. Even today, stars occasionally pass relatively close. For example, Scholz's star passed at a distance of about 0.8 light-years 70,000 years ago, skimming the outskirts of the Oort Cloud, fortunately without significant disruption. Such encounters, along with a constant weak pull of the Milky Way's mass, perturb the orbits of distant objects. Computer simulations conducted by researchers such as Alessandro Morbidelli show that these effects lead to the randomization of the Oort Cloud's orbital inclinations, transforming the originally disk-like distribution into an almost isotrophic sphere. The outer Oort Cloud, weakly bound to the Sun, was most susceptible to this process, and over time became spherical. In contrast, the inner part, the Hills cloud, more tightly held by the Sun's gravity, may not have become fully round and could have retained a flatter shape. Thus, the spherical form is a natural result of billions of years of gravitational influences from forces beyond the solar system. So you might ask, if our Sun has an Oort cloud, what about other stars? Astronomers do believe that similar structures should be a common byproduct of planet formation. The same processes, giant planets ejecting comets, stellar flybys shaping distant orbits, occur in other planetary systems as well. Scientists think that many, perhaps even most stars with planets have their own cometary halos, so-called Exo-Oort clouds. Indirect evidence supports this. When we detect comets falling onto other stars or debris disks with extended structures, it indicates that these systems also have distant reservoirs of icy bodies. In fact, our solar system may have exchanged material with other systems in its youth. Nevertheless, the direct detection of Exo-Oort clouds is extremely difficult, for the same reasons we cannot see our own. However, innovative ideas have been proposed. In 2018, a group of astrophysicists suggests that the large Oort cloud around a nearby star could leave a faint imprint on cosmic microwave background maps. The idea is that a shell of a distant cold, dust, and ice could slightly absorb or emit microwave radiation, creating a tiny shadow or glow detectable with a high-precision CMB observation. By analyzing data from such missions as Planck, they hope to find traces of such structures around other stars. After all, if a cometary cloud formed during the birth of our solar system, it's reasonable to expect similar structure throughout the galaxy. Each would be an invisible cocoon of material, a remnant of planet formation, and a source of occasional comets for its star. So what can we say about this grand object? At the very least, It's a fascinating paradox of modern astronomy, a massive structure we cannot see directly, yet one whose existence we are confident in. It's a testament to the power of scientific inference. Just as Neptune's existence was deduced before it was directly observed, Jan Oort inferred the existence of this distant place from the patterns of cometary orbits. And today this concept is only strengthened by new evidence, confirming that something is indeed there, even if it remains hidden from our eyes. On the threshold of the 21st century, we have yet to send a probe capable of reaching this remote place, and we've not built a telescope powerful enough to photograph its components. But the next time you see a comet light up the night sky, take a moment to acknowledge the profound reality of its origin, a cosmic halo which, though shrouded in darkness, illuminates our understanding of where we came from and how our system fits into the vast galaxy beyond.